Okay, good day. This is Math 140 College Algebra. I'm Professor McCully. This is Lesson 5-4, Partial Fraction Decomposition. Let's get right to it. Today we're going to recognize partial fraction decompositions of rational expressions, and we're going to find a fraction decomposition of related expressions. So before we get started here, we're going to talk about adding fractions. And when you add fractions, you're going to find a common denominator. And so just as a kind of an example here, if I had 2x plus 3 over x plus 2, I would have to find a common denominator. And that common denominator would be the product of these two denominators, the denominator x and the denominator x plus 2. And so I would go x plus 2 over x plus 2 times 2 over x, and then to this one I would go 3 over x plus 2 times x over x. I would get 2x plus 4, and then it would be plus 3x all over x times x plus 2, which would give me a final solution of 5x plus 4 all over x squared plus 2x if I simplified. Okay, in the last video I didn't simplify because we were looking for vertical asymptotes, but in this particular instance I have this. And so what I want you to see is to see that this denominator right here, and we'll call it the new denominator, is a product of the old denominators plural. All right, so what we're going to be doing today in our lesson is we're going to be taking something that is like this, a single fraction, and breaking it down into two fractions. So how do we do that? Well, our process is this. If we have a rational function, which is the quotient of two polynomials, first you got to divide the fraction if it's improper, meaning that the degree of the numerator has to be the smaller than the degree of the denominator. If it's not, you have to divide that, and then the result, whatever the remainder, whatever's left, then you could do it into impartial fractions. Now, in my two examples that I have today, I don't have an example of that, but you should get an idea. Then you're going to factor the denominator, and for each linear factor of the form px minus q to the m power, the partial fraction decomposition must be include the following sum of m fractions. Now, if you only get a single version of that factor, you only have to put it once. But if it's like squared or to the third power, you have to go a sub 1 over px minus q to the first, and then plus a sub 2 px minus q squared. And then if there's like to the third, you have to do it one for each degree. One for the first degree, second degree, and third degree. And then for each quadratic factor of the form x squared or ax squared plus bx plus c to the n, the partial fraction decomposition must include the following sum of n factors, must include all of those if this thing can't be reduced any further over the real numbers. Okay, so what does that look like? Let's start with an easy one. And just like in the last one, what we're going to do is we are going to start by factoring this expression. Okay, so this thing here is going to be x minus 2 on the top, and then let's see here. Two factors of 3, positive 3, that add up to positive 4. That's pretty easy. You get x plus 1 and then x plus 3. So the partial fraction decomposition, since there are no squares on either of those, I only need a term for x plus 1 and a term for x plus 3. So what we're going to say is x plus, or excuse me, let's not have a copy error there, Macaulay. So I've got x minus 2 over x plus 1, x plus 3, And then I need, and so my partial fraction decomposition is going to be two fractions. It's going to be the x plus 1 and it's going to be the x plus 3. And what I don't know is the numerators for these two new fractions. So I'm going to put an a here for this one. I'm going to put a b there for my second one. All right. And so what am I going to do next? I am going to multiply both sides by the denominator of the fraction on the left. So x plus 1 times x plus 3. Now, you know what? I'll write it out. So x plus 1, and it's going to be small, and I apologize for that, x plus 3 times this whole thing. So x minus 2 over x plus 1 times x plus 3 equals a times x plus 1 plus b times x plus 3. All right, so I'm distributing this x plus 1 times x plus 3 to these two terms. Now, when I multiply this x plus 1 times x plus 3 times this first fraction, the x plus 1's cancel and the x plus 3's cancel. And what's gonna happen is that's just gonna leave me x minus 2, and I wrote it again incorrectly, so let's erase and write it correctly. It's going to leave just x minus 2 on this left-hand side. Now, when I multiply x plus 1 times x plus 3 times a over x plus 1, the x plus 1's are going to cancel, but I still have to multiply x plus 3 times a, so I'm going to go a times x plus 3. All right. Now, when I multiply x plus 1 times x plus 3 times b over x plus 3, the x plus 3's cancel, but the x plus 1 doesn't. So I'll be b times x plus 1. So now I'm going to simplify this a little bit. And specifically, I'm going to distribute. All right. And that'll give me x minus 2 equal to ax plus 3a plus bx plus 1. All right. So, oops, plus b, because b times x is bx and b times 1 is b. All right. So here's what I'm going to do. I'm going to collect x's and constants. And so you'll notice that I have x minus 2 equals ax plus bx plus 3a plus b. All right. And so you'll notice I have a plus b, or I don't want that x. I have a plus b times x, and then I have 3a plus b and x minus 2. And so if you notice, this is in front of the x, I have a 1. So a plus b has to equal 1. And for my constants, I have 3a plus b has to equal negative 2. All right. Well, we can solve this a number of ways. We can solve by three ways. We can do substitution, we can do elimination, or we can do matrices. Whichever one you like. So I'm just going to multiply. I'm going to do elimination just to do it real quick because my b's will cancel. So I multiply this by negative 1. That gives me negative a minus b minus or equals negative 1. And when I add those two, I'll get, let's see here, 2a equals negative 3. That means a has to equal negative 3 over 2. All right, so if a, and I should use capital A since I had it in all those terms. So if a equals negative 3 over 2, I can go back to this original one. Negative 3 over 2 plus b has to equal 1. And so when I add 3 over 2, I get b equals 5 over 2. And so A is negative 3 over 2, B is negative 5 over 2. So my final answer, remember we're trying to solve for this, my final answer will be x minus 2 over, it was x squared plus 4x plus 3 is going to equal negative 3 over 2 over x, what did I put first there? Sorry, x plus 1, better job, x plus 1, and then 5 over 2 over x plus 3. And it's okay for us to have fractions there, as long as I didn't make a mistake. All right, let's do one that's a little bit more challenging. This one's going to have multiple fractions, and it's going to have squares in it. So similarly, I'm going to factor this, and that'll give me x times x minus 3 times x plus 3. And I'm going to leave the top alone, so x squared plus 12x minus 9. And so now when I set that up, x squared plus 12x minus 9 over x times x minus 3 times x plus 3. I have to have an a for the x portion of the denominator, and I have a b for the x minus 3 portion of the denominator, and I have a c for the x plus 3 portion of the denominator. And so now I'm going to multiply, that's an m, it's not a very good m, let's do a better job, multiply both sides by x times x minus 3 times x plus 3. I'm not going to write that out this time because we did it in the last one. But when I do multiply both sides by x times x minus 3 times x plus 3, this x times x minus 3 times x plus 3 cancels out. I'm left with just x squared plus 12x minus 9. And then when I multiply x times x minus 3 times x plus 3 times a over x, the x's cancel, and I'll have a times x minus 3 times x plus 3. And then b, when I multiply b over x minus 3 times x minus 3 times x plus 3, the x minus 3's cancel, and I'll have x times x plus, or just minus 3, x minus 3. So I do have x plus 3 because the minus 3's cancel. And then when I multiply by c, I'll have c times x minus 3. All right, so here I'm going to simplify a little bit. It's not very good. Simplify, okay. And that'll give me ax squared minus 9a plus bx squared plus 3bx plus cx squared minus 3cx. Yeah. And so let's collect x squareds, x's, and constants. So I have x squared plus 12x minus 9, and I'll have ax squared plus bx squared plus cx, and then I'll have plus 3bx plus, or excuse me, it'll be minus, and plus cx squared plus 3bx minus 3cx, and then my constants will be just negative 9a. Use a capital A. All right, so when I factor the x squareds out, I'll have x squared plus 12x minus 9 equals x, or excuse me, let's go parenthesis, and this will make it easier for us to see, a plus b plus c x squared, and then plus 3b minus 3c times x minus 9a. So you'll notice, and I'm going to highlight this here. This right here corresponds to what's in front of the x. This value right here corresponds to what's in front of the x, and then this value here corresponds to my constant because it doesn't have any x. So I can set up a system of equations that fits that. I can say that a, oops, I don't want red, I want black. Let's do black. I can say that a plus b plus c has to equal to 1. I can say that 3b and then minus 3c has to equal to 12. And I can say that negative 9a has to equal to negative 9. And that's a system of equations, and I can use that to solve. And we could do that a number of different ways. We can do substitution. We could do elimination. Or we could do matrices. I'm going to do elimination. I'm going to tell you how I would set up my matrices if I were going to do this. And the way that I would do that is I would go, let's see here, my matrices, if I was setting this up. I'm not going to do it that way. If I was setting it up, I'd go 1, 1, 1. I would go 0, 3, negative 3. I would go negative 9, 0, 0. And then I would go 1, 12, negative 9. You could do it that way if you wanted to. But I can solve this simply or fairly quickly, just algebraically, because this last one here only has an a in it. I mean, a has to equal to 1, right? And if a has to equal to 1, then I can go up to these top two, and I could say 1 plus b plus c has to equal to 1. That would mean that b plus c has to equal to 0. And then 3b minus 3c has to equal to 12. All right, so if that's true, I could do an elimination, and I could say, I could multiply this thing by 3 and say 3b plus 3c has to equal to 0. And now I can solve this and say 6b has to equal to 12 because my c's cancel out. All right, and then b would have to equal to 2. And I could go back to either of these two here, and we'll just do it to this one. I could go 3 times 2. I could just come over here. 3 times 2 minus 3c has to equal to 12. Well, 6 minus 3c equaling to 12. Negative 3c has to equal to 6, meaning c has to equal to negative 2. So now I know what a is, I know what b is, I know what c is. I can go back to my original setup up to here, right here. I had a over x plus b over, what was it, x plus 3 for the first one, or x minus 3 plus b over x plus c, and that should be a c there. Oh, totally screwed that one up, so let's just erase. C over x plus 3, and now I know that a equals to 1, so I've got 1 over x. I know that b equals 2, so 2 over x minus 3. And I have c equals negative 2, so I can put a negative 2 there, or I could have made that one negative, doesn't matter. X plus 3 over there, and there is my partial decomposition for that set of fractions. All right there, folks, that's all I got for today. So the Marvel fun fact of the day, to get ready for the Eternals, Kumail Nanjiani, I think I said that right, went on a strict low-carb diet and exercise routine, working out with Grant Roberts, trainer and former Mr. Canada. Nyanji would work out 5 days a week for 3 months straight at Granite Gym in Beverly Hills. His goal was to gain 20 pounds of muscle, wearing wires for electrostimulation that would help target the muscles. And you can see it's actually after and before. So there's your before pic and there's your after pic. And he's getting ready for the Eternals. That's all I got for today, folks. That's it. Have a good day. Bye.